Okay, so Unit 1 of your second semester physical science course is waves. Here I'm going to go over the unit review and kind of cover the important highlights of what you were supposed to get out of this unit. So, as we know, waves carry energy, okay? And they can travel through many kinds of material. One of the most common waves you're familiar with is water. Another one is sound. We also have an array of electromagnetic waves like visible light, infrared, ultraviolet, gamma rays, radio waves, and those can really be used to enhance our technology. So, wave properties is the first thing that you looked at in this unit. And if we look at your different types of waves, so there are two big sort of umbrella waves that all waves fit into. So all waves are either transverse waves or longitudinal waves. Transverse waves are like ocean waves, so they bob up and down. By definition, transverse wave is one where the wave moves um, perpendicular to the way that the molecules are moving. So, in other words, if you can imagine this as water, the molecules are moving up and down while the wave itself is propagating left and right. Okay, that's why we call it transverse, because the motion of the molecules is perpendicular to the direction that the wave is moving. A longitudinal wave is one where the motion of the molecules is parallel to the way that the wave is moving. So, for example, if you crunch up a few coils of a slinky and you let it go, you'll notice that the actual coils are moving back and forth just the same direction as the wave is propagating. Okay, so those are longitudinal waves. Now, some characteristics of both of these waves that you learned are amplitude, which is how high above the medium point, okay? How high above the equilibrium point here, this orange dotted line, does the wave displace, okay? In a longitudinal wave, it would be sort of the how compressed are the coils of your, let's say, your slinky as an example. Okay. The wavelength is the distance, as you know, between two crests or two troughs. And the frequency is how many waves will pass by a point in 1 second. How many waves will pass by a point in 1 second? So, those are some characteristics of waves. Then you looked at the difference between mechanical and electromagnetic waves. So mechanical waves carry energy through matter. They have to have some sort of medium that's made up of matter, that's made up of molecules, in order to be able to move from place to place. Sound waves are mechanical waves. They have to vibrate the air molecules in order to move from your instrument to your ear. Okay. Electromagnetic waves, they don't need matter. They can move through matter, but they don't need matter as a medium to travel. They can also travel through what we call a vacuum, which is just empty space. Okay, so you're going to go ahead and complete that for practice. Then you looked more closely at wavelength, frequency, and energy. Okay, so a wave's energy varies directly with its frequency and inversely with its wavelength. So let me explain to you what that means. If a wave has more energy, then its frequency is higher. That means more waves can pass by a point in 1 second. Well, if there's more waves passing by a point in 1 second, then the waves must be really close together. And if they're really close together, that means that their wavelengths are really short. So high energy waves have high frequencies, okay? inverse wavelength, meaning they have short wavelengths. If you have a wave that's really low in energy, that means after one wave passes, it's going to take a long time before the next wave comes by. So the frequency is really small, but the wavelength, the distance between one wave and the next wave, is really large. Okay. Then with frequency and wavelength, we can now talk about the speed of a wave. Okay, the speed of a wave can be calculated by multiplying its frequency by its wavelength. Okay, so velocity equals frequency times wavelength. So this relationship shows that if a wave travels at constant speed, its frequency and wavelength are inversely related to each other. Again, as you increase the frequency, you decrease the wavelength because they're much closer together. And as you decrease the frequency, you increase the wavelength. That's what inversely related to each other means. And you'll watch this video and that will help you with that idea. Okay, waves change speed when they pass through different mediums. Waves change speed when they pass through different mediums. Their frequency doesn't change. So let's say a light wave is traveling through space and then all of a sudden it hits our atmosphere or hits water. It is going to change speed. When a wave goes from air to water, it slows down. Okay. The frequency of that wave doesn't change. The frequency is from the source. It depends on the source of the wave, okay? Not the medium. So the frequency doesn't change. The speed of a wave is its frequency times its wavelength, which we already talked about. So what you're going to do is complete this activity, keeping in mind the idea that velocity depends on frequency and wavelength. And the frequency doesn't change when it changes mediums. The frequency depends on the source that it's coming from. Okay, interference. When waves interact with each other. So this is like, what if two waves get to the same space at the same time? What happens? Do they just not interact? Do they make one huge wave? Do they cancel each other out? What happens? Okay, so that's called wave interference. When you have two crests meet, that's the two peaks, what happens is you get a much bigger crest. That's called an additive property or constructive interference. Constructive interference means you get a bigger wave, okay? When two troughs meet, the same thing happens. You get a much bigger troughs. Now, for longitudinal waves, so remember those are the slinky type of waves, the way sound travels, constructive interference results in denser compressions. That means you just get a louder sound, okay? Electromagnetic waves. So then you learned about characteristics of electromagnetic radiation. They differ in energy and frequency, but they're all made up of photons, okay? Now, you also looked at what's the difference between a wave and a photon. We call it the wave-particle duality idea. Instead of causing particles in matter to move, electromagnetic waves carry energy by causing vibrations in an electromagnetic field. Okay, it says watch the video to review the characteristics of electromagnetic waves. This will help you review that. So this is the electromagnetic spectrum I was talking about earlier. Different wavelengths or frequencies of light, different energies of the electromagnetic spectrum can penetrate through different densities of medium. Okay. Here you can explore this electromagnetic spectrum more. You can click on one of these and it gives you definitions and what this type of wave is used for. So like, microwaves can be used in communication, like cell phone signals. They can also be used in cooking. Infrared is really heat. They could fit through the eyes of a needle. Warm objects such as the human body produce large amounts of infrared radiation. And then, of course, we have visible light. This is where all the colors of light that our eyes are sensitive to exist, between 400 and 700 nanometers. And then ultraviolet, we can't see. Ultraviolet waves have higher frequencies and shorter wavelengths than visible light. Humans use ultraviolet waves to sterilize surgical tools. You probably have heard of this a lot during the COVID pandemic, where businesses, even our own school, has UV light that can sanitize things and sanitize the air to keep air cleaner. And then there's X-rays, which I'm sure you've heard of. We use this in imaging of tissues and bones. And gamma rays. Gamma rays are the highest radiation. These are actually quite dangerous in large amounts to the human body. However, they are used in the medical industry to treat cancer. They're used in the industrial process that requires sterilization of equipment and disinfecting of food. So that is the electromagnetic spectrum. You then looked at the idea of transmission, absorption, and reflection. When electromagnetic waves encounter matter, they can do a few things. They can either be transmitted, that means they pass through that medium, absorbed, or reflected, depending on the type of matter and the wavelength and frequency. Okay, so here you're going to discover or play with transparency, color, and temperature. You can see underwater because of the transmission of visible light. So it goes through transparent water. Transparency is a property of matter that transmits visible light. So if something is transparent, it can pass visible light through it. Okay, air, glass, those are transparent materials. Water absorbs many wavelengths in the microwave and infrared region as well. Okay, now color. Color is like an apple appears red because it absorbs all the other visible light rays except red. It reflects red. So the only way that you can describe something as red is if red photons or red wavelengths of light reach your eye. And the only way that red wavelengths of light can reach your eye is if they are reflected off of the object that they hit. So when, let's say, sunlight or the light inside your house hits an apple, that light contains all the visible light wavelengths: red, orange, yellow, green, blue, indigo, and violet. But a red apple absorbs all the other wavelengths, but it doesn't absorb red. It reflects red. That's what reaches your eye, and that's why you describe the apple as red. White objects reflect all of the light. So they all reach your eye at the same time, and you see it as white. Black objects absorb most of the wavelengths, and so none of the colored wavelengths reach your eye, and so you don't see any of the colors. That's what black is. Temperature. So brown fur on this dog's head absorbs more visible light than white fur. Okay, so white reflects and black absorbs. That's why they say in the summertime wear light colors, because it will keep you cooler, because it reflects a lot of the infrared radiation, whereas black would absorb that thermal radiation. Okay, the wave model of light. So this section discusses the idea that electromagnetic radiation exhibits many behaviors of waves. If you use the wave model of electromagnetic radiation, it can have a lot of uses in explaining these behaviors. So if we're looking at these images, for example, this wave, one with the light, it says beams of light pass through each other without changing. color, path, and brightness of each beam is the same before and after the beams pass through each other. If you look at streams of particles, separate streams of particles, such as these two colors of sand, cannot pass through each other unaffected. Instead, the moving particles collide and mix together. These collisions change the path of the sand particles when the streams intersect. Okay, so that doesn't happen with waves. So you should look through this and explore this a little bit more to get a better grip on looking at the wave characteristics of light. That brought you to the photoelectric effect and the particle model of light. Okay. So, yes, light waves behave like waves in many ways, but in some ways, it's a lot easier to explain phenomena and to use the technology if we can look at light as streams of particles instead of waves. Okay. The photoelectric effect is one particle behavior of light that we can look at. So, take some time to play with this animation. It says turn on the switch to observe the photoelectric effect as light hits a piece of metal. So you turn the switch on, the light goes on, the light shines on this piece of metal, and you can see electrons are excited and begin to move through the wire. So electricity begins to flow from the metal, the light changes frequency. The light changes frequency. Okay. So this is what I was talking about earlier in the video, the wave-particle duality. That's a very fancy name for quite a simple idea. And here's the idea. Electromagnetic radiation behaves both as a wave and as particles. Okay, those particles we call photons. The wave model and the particle model are both correct. It just depends on the application. Again, here's another activity that you can use to kind of look at the wave and particle properties of light. So this actually helps. This is like sort of the wave. You can see two waves. One's on sort of the x-axis here, and one's on the y-axis, the red and the blue. Electromagnetic radiation travels as waves. That's according to the wave model. And it causes disturbances in the electric and magnetic field. If we look at, and so looking at the wave model, we can look at things like diffraction and interference and things like that. If you look at the particle end or the particle definition of light, electromagnetic radiation is made up of a stream of particles called photons. They're extremely small, they're packets of energy, and each little packet of energy contains a different frequency based on the amount of energy that packet is carrying. The ones you see here in this picture are orange. So they have the orange frequency or the orange amount of energy. If they were purple, they would be higher energy. If they were ultraviolet, they'd be even higher energy than that. If they were infrared, they would be much lower energy than orange. Okay. Behaviors like black body radiation and the photoelectric effect can be explained only by looking at the particle model of light. All right, so what are some applications of waves? We're going to look at how are waves used in technology, in our digital world, in our analog signals, and all the ways that we use them in our world. So electromagnetic waves in the radio and microwave frequency, like we mentioned before, can actually travel really long distances without changing. And they can pass through solid objects. So this makes it really useful for us in communications. Okay, so those are used in communications all the time. Again, explore this image on your own time and look at the different electromagnetic frequencies in the communication world. So AM radio is here, FM radio is here. This is all our TV, cellular, and Wi-Fi in the ultra high frequency, and then satellites and GPS use super high frequency. Okay, so explore that a little bit more. Cell phones are one application. They use radio signals to send and transmit information. They depend on a cellular network of antennas that communicate directly with other devices, like phones. They also communicate with fiber optic cables. Okay, so you're going to want to look at these things. How is the signal transmitted? How is the cellular network used? I think you can tell by the pictures here. And how is the data received to my personal device? Like if someone likes my Instagram post, how do I see that they liked my Instagram post? Okay, so there's a lot that goes on behind that, and this will help you understand that a little bit more. Scanners, you've seen these all over the place. There's computer scanners, there's barcode scanners, and there's security baggage scanners like the ones that you see at the airport. These use electromagnetic waves to read information. Again, many applications in technology. The video would be too long if I went over all of these in detail. But go ahead and read through this. They're actually quite interesting. Like in a document scanner, says they contain light that shines on a photo or document and a charge coupled device called a CCD. This collects the light reflected from the object, and then it releases electrons through the photoelectric effect. Light falls on them. Brighter light, greater number of electrons released, and therefore you get an image. Okay, barcode scanner. Again, the red light reads the black and white barcodes, so read through that to see how those work. And then, of course, the security baggage scanners as well. Okay, so that will be helpful for you to read through. All right, analog versus digital. All communication technology relies on either analog or digital signals to transmit information. And this is an activity that helps you determine which is digital versus analog. Okay. So you can practice that to determine the difference. And then storing digital data. Most information technology today stores data in digital form. You already know that. So these are some applications of digital storage, digitized data, like pixels. You've probably seen pixels if you're shopping for a TV or a monitor or a cell phone that has really good resolution. So this helps you really understand what's a pixel. And then storing data in like a microchip, like how can phones get smaller and smaller and smaller? Well, because they're figuring out how to store more and more information on a smaller microchip. Okay. And then binary code, ones and zeros to kind of, that's what everything is. All digital code is ones and zeros in different combinations. So this will help you understand like pixel numbers and things like that. And then lastly, transmitting digital data. Although electromagnetic waves have a continuous range of frequencies, they are commonly used to transmit digitally coded information. Okay, so this shows you the difference between fiber optic cables and wireless transmission. You can see there's not much of a difference here, but the flashes of light that you use, like if you've ever used your flashlight to send someone a signal or Morse code or something, those flashes of light carry a code. The same thing is true for fiber optic cables. They send digital data through infrared light. Okay, that's like heat. The code of ones and zeros, that's the binary code, is produced by a wave pulse, and then lasers send very fast pulses of infrared light into the cable based on the code of ones and zeros that they received. Wireless transmission, so this is all your Wi-Fi at home, the way that I'm communicating with you at school, all of that. Radio waves are used to transmit digital signals. The properties of these waves are modified so they can represent ones and zeros. Okay, so it gives you an example here. The wave amplitude can change to transmit binary code, right? So 1 would be a really long amplitude and 0 would be a really short amplitude. And so you would get this code of 1s and 0s just based on the amplitude of the wave, okay? So that's how you transmit digital data. I hope you found this helpful. Please stop by or shoot me an email and let me know if you need help, and we'll figure out a Zoom time to meet.